Durgesh. Good morning. Okay, 8:03 is our magical start. Okay, hit the magical 8:03. So let's get started. It's amazing how critical mass actually magically shows up at 8:03. I don't know what that is, but that was a boppy thing which we keep going. Today's agenda was basically having Durgesh talk about system level issues he has actually faced. So for someone who's integrating chiplets from multiple vendors, not just looking at die-to-die interface, that's just the hardware portion, but above that, putting together a system with the software, security, bring up very good points, which I think is important for us to think about and discuss and maybe come up with solutions if we need to. So that's agenda item number 1. The second piece, if we have time, was to continue the discussion from last week on the proof of concept. JP shared the Chiplet idea, which was essentially chips on PCB. How do we extend that to a prototyping board of some sort where people can actually test their wares in a system? So that's the second topic of discussion. That that's going to probably be a long topic. So we might have to go through multiple sessions to get everybody's opinion on it. But I think I would really like everyone to think about this and ideas that you may have. Ultimately, to prototype anything, we need some dollars. So we need someone to actually contribute more than kind, actually money to manufacture something. So it's it's a little more difficult proposition than writing a white paper or contributing in kind. But I think it's important for us to think about that if you want this to be more of a reality. So that being said, Durgesh, it is all yours, and it's an open for discussion. He's not going to have a whole boatload of slides, but the idea is let's talk about it. Thank you.
Thank you, Anu. Yeah, hi everyone. My name is Durgesh Srivastava. I work at MIPS. I joined a year ago as CTO for MIPS. Prior to that, I was at NVIDIA for around 3 years, and then prior to that at Intel for 20 plus years. So my background is more silicon architecture and systems with a lot of focus on the data center. I worked on automotive also briefly for a couple of years, but most of my time I have spent in the data center, silicon and systems architecture. So I talked to Anu and Jawad on some of the
Oh,
challenges.
Steve, they move things around.
Um, that was not a question, I'm assuming. Um,
I think it was someone by mistake off mute. So
okay. So the reason I was talking to Anu and Jawad was that moving from bigger companies to now a 200 people company with limited funds, we wanted to do a chiplet based solutions, a full solution, and the challenges we face. So proposal is just to brainstorm here, like knowledge sharing and problem framing, as I called it loosely. So system level challenges, which is beyond, say, UCIe or bunch of wires, and looking at a package level solution, which can go in the production. And this problem is amplified when there are multiple vendors involved, as people have built their own chiplet for different needs and they're trying to reuse. So I want to cover that. Let's collect all the inputs and then we can brainstorm towards the end what's the best way to do and collaborate it so that we can help grow the chiplet ecosystem. In the end, all of us, our vision is to have sort of catalog of chiplets where you can pick from various vendors, put it together, find a vendor who can package it, test it, and you can get it out. That's the ultimate Uber vision. And if we can achieve it, then we will have a lot of innovation in the silicon industry, as the cost of developing a chip will go down. Any questions on this? Okay, so I abstracted what we were trying to do. So on the left side, you see the pink block is the MIPS, what we are building. And I was primarily hired to build the chiplet because MIPS historically is a IP company. So we provide the IP and then SoC vendors build their own chip. But my role was to build a AI processor using RISC-V open ecosystem, and not having proprietary solutions. So we have a solution working on FPGA, and we wanted to build it as a self hosted, which means that the OS can run on the ping system, which is the fully RISC-V compliant, and required some of the South chip, or in Intel terminology used to be ICH, then became IO Hub. Things like SPI controller for boot and interrupt controllers, PCIe. So some of the basic peripherals which can be on the older process technology. So that's the chip we wanted to build as a self-hosted AI product, both for automotive and the data center space in the inference. And that's what we investigated. And that's what you see is left as a single package. But as we start working between the our partner who had a blue portion of the chiplet with a different interface, and we had UCIe, and this is a 2D, not advanced packaging on 5 nanometer. There were a lot of problems which we faced, which I'll go through, whether it's through the boot sequence, which we were trying to define, security, testability. So it became so complicated that we decided to go initial product as option 2, where we are just packaging the MIPS chiplet, which is, of course, production ready and auto certified, but we found a known package which is cheaper and we package it. We bring UCIe on the PCIe, sorry, on the PCB itself, and then system chiplet, instead of using the chiplet, we decided to use a FPGA because we have an FPGA where it's functional and overall TCO ownership. And instead of making a production chip, we converted it into a reference platform for now. till we resolve some of the issues, and then we can make a full package out of it. So I want to pause here as I provided a lot of data. This is abstracted version of what we are trying to do. But as you can see in the pink portion, it's a quad core processor. Each core has 2 threads and independent L2. L1 and L2 is not shared independent, and L3 is the shared with a LPDDR5 memory with UCIe. So not that complicated per se. Is a very standard, but the vector and matrix are the bigger portions of our chip. So that matrix especially is the biggest portion, which takes more than 50%. Any questions on it before I jump into the next slide?
Quick question. You mentioned RISC-V, so this is based on RISC-V architecture?
Yeah. So our company name is MIPS, but we have fully pivoted to RISC-V just to join the full open ecosystem. So all the processor is RISC-V. Vector is also RISC-V RVV. Matrix is not closed. There are 2 directions right now, but we picked one of those and we have implemented it.
So Durgesh, one question, I guess 2 questions. In the option number 2, you have the system chiplet that is in blue. So you said this is implemented in an FPGA, right?
Yeah.
And then, so I guess that my question is, this interface that is showed with arrows, is that a new CIE interface that you have also in the FPGA, or how does that one work?
Yes. So for the 2D, our trace length or the between microbump to microbump, we design in a way that we can bring the UCIe on the PCB. We don't think we'll need retimers, but if that does not work, we are still doing the signal integrity, but we want to bring UCIe itself on the PCB and then connect it to the FPGA directly so that we don't have to reconvert into another protocol and add the additional latency. Did that answer your question, Lisa?
Yes, for the most part. I guess my on the FPGA side, what does the interface look in the FPGA side? I imagine this is a commercial FPGA.
Yeah, so Xilinx has a solution which has UCIe.
Oh, okay. Yeah, okay, that makes sense. And then everything is engineered such that you can go through PCB. That's what you said.
Yes, and
Okay,
we're just
I see.
trying to butt it together so that the trace length between those two works out. So that's where we are working right now. But that solution is much cheaper than the option one for now. That's where we are at.
And how far did you go into option 1? Did you get to get a model of this, or you
We
just stopped at the abstraction?
went a lot in the architecture deep dive with our partners. This was a Taiwanese company, so we had 2 face-to-faces. But we felt that the amount of changes and the things we are trying to do will push it out by 6 months. So we decided to go for a reference platform, which is option 2.
Thank you. Yeah, that answers my questions.
Yeah, and the other challenge, just to highlight, is that the system chiplet, which I call on the left, and right, I will change it to FPGA. The other challenge was that they already had a chiplet which was working with another product. So it was not designed for us. So yes, there were some retrofitting challenges, but in general, that's the goal, that you design chiplets as a catalog and then you can put it together. So that was a good learning experience, that it was pushing out the schedule.
Hey, Durgesh,
Yeah.
this is Raghu. That for that UCIe interface to that system chiplet or FPGA, are you using a lot of the UCIe capabilities? I'm curious as to what UCIe capabilities you're using to go, especially UCI comes in multiple modes or 3 modes that we are aware of, right? So
This
is
is
there any?
Chai. We are not in the pass-through mode, not the raw mode. We are using the Chai protocol. So our NOC is Chai compatible. So it goes in the Chai through UCIe. So the first layer, the FDI layer, does add the header for chai and does all the error corrections, and same thing on the FPGA. So that's why we didn't want another protocol conversion. But so it's a chai mode, not CXL and PCIe. But the FLIT is 256 byte FLIT.
Okay, all right, thanks.
Yeah, so it's essentially, Durgesh, it's the 5 plus a die-to-die adapter, and then the protocol layer to get you your chai.
Yes. Yeah. And we are not in the raw mode where you ignore the digital portion of UCIe 5.
Yeah.
The FDI layer, we do use it because we are using the chai 256 byte FLIT mode.
Okay. And then in your option 1, I understand, it was difficult to put together and cost-wise. Ultimately, you want to use some form of advanced packaging, I'm guessing. Do you have an idea of what that would be?
So Anu, as I was telling you, I would love to do advanced packaging because that's the word I came from Intel and NVIDIA. But when I look at the 2.5 advanced packaging with the interposer, tape out, everything, the cost is prohibitive. So the first production part will be 2D, in spite of all the challenges, just the business. I would love to do 2.5, but right now, based on the customer needs and where we are at, we will just go with the standard packaging.
Okay, understood. Thank you.
Hey,
Um,
Durgesh, sorry.
No, go ahead, Anshu.
So 2 questions. One was, so this in option 1, the system chiplet was not FPGA. Sounds like it was something else, right?
Yes, it was. So the Spring portion is 5 nanometer. This was 12 nanometer system die, which was functional in a different setup without technology partner.
Okay. And
Who's this?
sorry.
Anshu, please finish. No.
Yeah. The other question is, these
Selling my house? No, thanks. Bye.
these 2 chiplets are basically monolithic, right? The MIPS and the system chiplets, or are they?
No, they are monolithic in the sense that each chiplet is just one chiplet. So it's
Okay.
a quad core. It's not that each core is a separate chiplet. Yeah.
Okay. And finally, I guess you've sealed option 2. You won't go back to option 1 sometime in the
No.
future.
We have to go back to option 1 at some point because that's the production. So instead of production, we just went for reference because developing the software and providing it to customer is hard on FPGA. We have very good capability in FPGA, but it's hard because we are doing in the single core mode, all those things. So option 2 is a quick reference platform, but I want to go back on option 1 for the production platform, which gets deployed.
Okay, thank you.
Hey, one more question, Viresh, and this is more of a go-to-market question. So who is going to be selling the option 1?
Yeah,
That'd be MIPS.
John, it's a very important question. In the reason I am not able to answer you directly is because we're still figuring that out, because there could be 3 options. One is MIPS, we white label it and the third party does it, or the blue portion of the people do it, but they don't want to, they don't have the capability. And third option is that we do it. So first option, maybe let's rephrase. We do it. Second is the blue people, or the third is we white label and someone else does it. So that go-to-market is still figuring out. And because, again, all the challenges which I'm going to cover in the next slide, it becomes very complicated and open. So it buys us some time to resolve those.
Understand and agree. Yeah, it is complex. Thank you.
Yeah.
I would have one more question. Thanks for the showing this and the great discussion here. Coming back to this UCIe interface, if you're bringing this out through the package rather than having this on package, I'd be curious, like anything you can share on making that work. Like, did that mean maybe reducing the lane speed in order to meet the signal integrity performance, or was it at all a challenge to basically use it for a purpose that it wasn't designed for initially?
Yeah, so give me a month. I can bring back all the technical learnings on that front for sure. We are doing some of the signal integrity analysis, and we don't want to add retimers because retimers, if we add, we know we can do it.
Right.
As there is a mode for retimers. I mean, the raw mode was designed for retimers. But let me finish it and then we'll bring it back here and we can go through it.
Awesome, thank you.
Yeah, no, that's actually a great question because most people, the UCI would be on package.
Yeah.
And you're actually putting it in theory, Marek, according to the spec, if you're less than 25 millimeter, and because it's a standard packaging, you shouldn't have too much of an issue with signal integrity. But that's a theoretical KPI. I don't know.
Right, and I guess like just a lot of signal transitions, like going through at least a number of layers in a substrate. Like I could imagine that still is not trivial.
It is not, even though UCIe spec, I was involved in that, and UCIe spec was that retimers were made for it. But first, there are very limited options, and then it is very expensive. And again, when you are in a 200 people company and it's a re-startup, even though it's an older company, but it's a re-startup, you have a lot of cost constraints. So we are going through that and doing all the evaluations to make it happen.
Got it. Thank you.
So, Durgesh, one question. When you moved from option 1 to option 2, it looks like that you have one piece of silicon per package, but you decided to keep the name Chiplet.
That's a typo. I made this only last night, this slide, the remaining slides I had. So I should call it FPGA. That's a good catch, Jawad.
Okay, great, thanks.
Any more questions? Okay, so this is a longer list. It's not just our experience. I've been talking to a few others, and I am involved in Chiplet for some time, and I'm passionate about it. So I start collecting all the other problems which people are facing. And then John was asking about who will stamp the package as the owner, because the RMA is the return to manufacturer. All those things have to be taken care of. So there are a lot of things which keep coming in and good learning. So I talked to a lot of people, including the Chiplet Summit, to understand how they are doing. And on the floor, there were a few people who said they have a package chiplet. Those are discussions we had. In my previous life, before MIPS, of course, all the chiplets which we worked on, they were built by the same company. So as you know, Blackwell, both the chiplets are built by NVIDIA, so it is much easier. Same thing in Intel, in Granite Rapids, all the chiplets are built by Intel. So that makes it much easier, but the goal was how we can build a chiplet economy where the chiplets are managed or produced by different vendors. So security, I put it on the top because if you want to go in data center or automotive, the security requirements are very stringent. And even just to decide what would be the trust boundary, whether it's the package or the chiplet, how do we do it, where the root of trust will be, and do we have multiple root of trust? That was a problem because I don't know my vendor's chip. So as company, we were worried that if we take the responsibility for the security, and especially in data center is confidential compute, which means the data at the storage, data at movement, and data at compute, all you have to secure. It is becoming difficult because a lot of data comes through the south complex, which is the SATA or the storage and the networking. So once it goes in the main memory, then it is in the MIPS chiplet, but once coming from network or the storage, then it goes through another chiplet. So we have some solutions, but it was not that straightforward. And when we look at what UCIe did is more at the interface level, not inside, and some of the challenges related beyond the interface, those were still open. And that was one of the things which we spent a lot of time, and we continue to talk about it, but we have not reached on a common conclusion on some of the very basic things, or what would be the trust boundary and how the 2 root of trust or even 4 root of trust engines will work with each other. Other learning was that power and thermal was very.
Lokesh, can we just spend a little time on security if you don't mind?
Yeah.
I'm no expert. I'm just trying to understand here. So, in a system of chiplets where chiplets come from different vendors, the assumption is the assumption that each one of them has a secure boot, or is there one chiplet in the system that should have the secure boot and the hardware root of trust, and that
Sure.
one then communicates to the others? What is the general philosophy? And I'm asking a question because I don't know.
Yeah, there could be both, but I'm talking more from the server and even client side, that what happens in the boot when you're booting, say, a Xeon server, for example, or Grace, which was my product, the root of trust comes up first. It authenticates, so it is ROM based, so it authenticates the RAM. And once it authenticates, then it will authenticate the spy flash. So it's a chain, right? You start with the basic and then keep going to next and next. So in general, the word I come in, there are multiple ways to do it, but the word I come in, always the CPU or the compute has the root of trust. It starts the authentication from root of trust, and then it does the next level RAM, and then other component like the chain from one to other, and then it hands over to the house complex. But most of the chips have multiple root of trust because they validate their own. Then they hand it over. But for my background, it is always the CPU complex, which is the master, you can say, which collects all the information, makes sure is authenticated before it hands over to the next chain.
Yeah. Hey, Durgesh, it's Cliff. Are you familiar with Project Calyptra?
Yes. So when I was at NVIDIA, I was part of the Calyptra. So we did implement Calyptra in Grace Next. But just so that you know, there were 3 or 4 other root of trust which are in the chip.
And did you see Calyptra as something that we could leverage here in this project?
I'm a strong believer that Calyptra, if it becomes the central root of trust or the first one which comes up, or the master in a way to say that, good solution.
Yeah, so Cliff, I noticed when Greg Selman from AMD presented to us on the new AI initiative that OCP has, he had the one line item on security and he had chiplets there. And I had asked the question, how does this tie in with the existing security groups? I don't think there's a clear plan, but maybe this is something that needs to be talked about. I don't know, in that group or in our group, but there's got to be some cross-pollination here, I think.
Yeah, so you can thank me for putting that line in there on chiplets and security.
I knew I could blame you.
So I snuck that in there because I know it's going to be essential, but I would say at this point, your conclusion is correct. Nothing's actually happened on it yet. And so once we're a little further along in our plans here for chiplet security, we can circle back and perhaps bring that to the larger group. But I'm looking for the Open Chiplet Economy Project to be the owner of that.
Okay, thanks, Liv. So Anu, you made a note, right?
Yeah.
All is back in your court.
Everything is back here. No problem. Got it.
I can help on the security, as I spend a lot of time on the Grace and Grace Next, and very familiar with Calyptra and very supportive of it.
That's great, because I have none of the above. So we would definitely need your assistance. So let's talk about it later.
Yeah. Second thing which we hit was power and thermal. We both developed the chiplet independently. So our partner, the Blue chip, was more implemented as a client platform. Like when I say client, more like a laptop, not even desktop kind of way. And for us, we implemented it more as a server kind of area, because automotive is also battery driven. So it's very thermal. sensitive, less so in the power consumption area. So that was another challenge on where are the power islands, and when we have the voltage regulators, how they are controlling it. Do we keep it separate? This one we made progress because this was a little bit easier in the sense the way it was implemented. But again, it's like a handshake between two chiplets rather than a standard or easy way of doing it. So this will be, as people develop more chiplets, they will also hit these kind of problems. Testability was totally off or is still off, so we didn't spend time on it. Inbuilt test were easy because you're doing at the chiplet level, but we go beyond the chiplet level. How do we do it? We have not spent time on it, but it was definitely a thing which we definitely should talk more about it.
So, Durgesh, and this is where the infamous words known good die show up, right? So the idea is to be able to produce enough of your known good die and the other known good die, and then put a fairly confident system together that you have good yield.
Yeah, so we didn't reach that stage. We were still defining how we will do, what would be the methodology, because we didn't even know who will own the package. MIPS will own it, or we white label it and the third party.
Yeah, no, I think that's an important place to figure that out before you.
Exactly. So we pushed it out a little bit, just kicked the Coke can out for now. Then power performance, I already touched. But from the power perspective, especially integrated voltage regulators versus just the voltage regulators, whether we do the DVFS kind of thing, whether we both change the voltage and frequency both. So some of those things were challenging in the South chiplet. There is no, there are power islands, so we can power gate it, but there is no voltage frequency challenge, which is still a challenging, but in a compute chiplet, you always have DBFS kind of functionality. So again, we can manage it. South complex, we can power gate it for the IPs which are not utilized. But this is again a thing which spans across multiple chiplet and not focused on a chiplet itself. Also, the number 5 reliability, given automotive and data center both have requirements, very high stringent requirements on reliability. And data center really hates SDC, and hate word is I'm using it loosely because when you have silent data corruption, it can show up after an hour when you're consuming the data and you have no idea what caused the silent data corruption. So a lot of those things were mismatch between those two, especially coming from different ecosystem, one coming from client world, another coming from server and automotive world. So that was there. Then aging, stress mitigation for automotive, robust error recovery, all those things were again a topic which we have not spent so much time on it, but it came up. We collected as opens and was challenging.
Yeah. Durgesh, I'm curious, are you familiar with a small company called Protein Tex?
Yeah.
Okay. I always wondered if some of their technologies could be a good solution here.
Yeah, so when I was in the UCI board, then we did talk about Protein Tex because they work very closely with Mercedes-Benz. And then afterwards also at MIPS, we have talked about it. So their solution could be useful. I have not looked at it as a solution. Just integrating that in the UCI, I'm just going vague, but yeah, there were some legal challenges also on the patents kind of thing. So I remember some of those things being discussed. And again, IMEC, I want to mention, given Cliff, the good point you brought, IMEC is addressing some of the packaging level issues, and we are part of that. We joined it for that reason for automotive, given we are targeting both. But IMEC is very much focused on the automotive and not in the other spaces like Edge AI, which is the growth segment, and industrial, those kind of things.
Hey, I have a question here.
Yeah.
Rajesh here. So one simple question is, assuming we got to somehow magically solve the problem of KGD and procuring the die. What do you think is the biggest challenge of system level test, in your opinion?
This is more or less in the order which we have faced. So at least in our experience, so security to go anytime in the automotive and data center, the security and who owns it, and integration was a problem, testability. So it's more or less in the order, Rajesh.
No, I'm just focusing on number 3. So in that, what is your, you think, biggest challenge on addressing the testability at the system level? Assuming we got some, because as you mentioned, right, the challenges of fault isolation, or is that the one you're more concerned, or how to enable the test from the system level software?
So fault isolation was a big item because you have to, automotive, you have to do the extended temperature and long life support. And then debugging was, then we have to debug jointly, right? We cannot say our chiplet is clean and yours could be the problem, but just debugging and enabling is another one which we have not solved it yet. We have a list of 7 items. Rajesh, I can send it to you, to this group, which we identified. I just took 2 just to keep it.
Okay.
Which one did you not solve?
Debugging right now.
What aspect of debugging?
Whether we, so once we provide the chiplet, right? Say we go TSMC, both of us, TSMC provides the die, and it's a known good die. And then OSAT is integrating it and doing the testing. So who will be responsible? Shall we both go together and debug it? Those kind of things, just to before pre-packaging and post-packaging debug.
Is it this on processors or other chips?
Kevin, repeat it one more time.
I was wondering, that just processor chips or general purpose chips?
Both the chiplets.
Okay.
Because 2 different companies work for two different reasons and trying to put the chiplet together, which is fully functional, or at least our chiplet is functional only on FPGA, but their chiplet is deployed in the industry, but in a very, very different working environment.
Mm-hmm.
Okay, in the interest of time, I'll continue going. So Rajesh, I took a note of your question. Definitely we should go in the detail. This was more of a preview to see how OCE can help in this. So this is more of a teaser, you can see it that way. Then interoperability, scalability, in the sense that we want to build multiple SKUs of it, where right now I showed you with the 4 RISC-V processors, but in one of the solutions we have 8 and then going to 64 in our roadmap. So we didn't spend a lot of time, but those are the things which keep coming up because all the micro bumps will change. And also as we go further, as we start selling, then we would like to go to advanced packaging, as Anu was asking. So some of those things, manufacturing and supply chain, we don't have that much expertise because we're a very front-end heavy team. So we're trying to pair up with a backend team to help us with it. So I just wrote down the things which you wanted to know and how the long-term support will be there. Thermal management, I talked about power, but thermal management was very coming specifically from the automotive perspective, because with the ADAS and automotive, I learned they call it HPC, high performance compute, which was news to me. But there's a lot of thermal challenges which are coming in. So we did spend a lot of time on it. So behind the power and power management and DVFS, those kind of things which we talked, there's the thermal challenges which are also coming in, and the cooling solution. Then you have to figure out on a package whether you're just going to go with a copper plate, uniform copper plate, or you have to redesign so that because the heat dissipation on the compute side, especially when the matrix is on, is a lot higher. So it's not a uniform. There are a lot of thermal spots. So those are the things which we have not reached yet, but that would be good to look at. This is not new even in the GPUs and other AI products. Even if it's monolithic, they have problem where there are hot spots which are very localized in spite of all the design. So something similar we feel that would be useful when you are integrating multiple chiplets with multiple functionalities. And the last one, which is latency optimization. So one thing is for debug, we want predictability. So if there is a failure which is happening, we want to reproduce it. And sooner the better, because if you have to rerun again 24-hour cycle and then you find it, that's a challenge. So again, between the chiplets, it has to work on the predictable environment where you can reproduce it and the behavior is as close as possible, or if you do the microarchitecture flush, you can still try to reproduce it. So in my past at Intel, I had done a lot of silicon debug for Xeons once working from the architecture team. So didn't go into detail on it. We are seeing that at least for our solution, we were able to narrow it down. This was not a big problem, we believe. So I put it as last, but for some chips, especially both the chiplets, if they're new, it could be a problem and something which has to be looked at. So this is a high level 10-item list which we created, and this is coming from a big spreadsheet which our program management tracks. I wanted to highlight the team here on the challenges on a whole to make the chiplet ecosystem easier to adopt. So to pause here before I go to my last slide on some of the suggestions.
So I had a question on the last one, latency optimization. When you've picked an interface and you've got UCIe listed, it comes with a certain latency, right? There is a KPI, raw data to raw data, or flit to flit. That is possibly the best outcome you can get. You can optimize maybe on the flit side, but on the raw data side, aren't you somewhat limited by the interface you pick?
So Anu, whatever I'm saying is beyond the boundary of the D2D interface. So I'm talking about, say, for us, certain accesses in the net, say networking is a priority. So I want the network data when coming from PCIe-based network to reach us as soon as possible. Whereas the chiplet was prioritizing the SATA data because the desktop or a client platform. So I'm not talking about the die-to-die PHY because that is known and addressed.
This is at a higher level. You're saying with the multiple layers.
Yeah. So because the goal is you just buy two chiplets and put it together. I mean, easier said than done. But here, that's one of the things which we hit because in their architecture prioritization, they will always prioritize the SATA traffic. And we will always prioritize the network traffic because we expect most of the data coming through DMAs and even RDMAs. So it may not be applicable to everyone. I just wanted to highlight what are the things which start showing up as you start putting two chiplets together.
No, understood. Thank you.
Okay, so it looks like I am way out of time. So mainly the goal was to engage OCP members. We all have the same interest coming from different areas of expertise and refine the problem statement. I don't want to just have the one which I gave as 10 as the key problem statement. We refine it. We also look at solutions and understand it better. I'll be more than happy to provide more details on experience on this as well as talking to some others. The options could be we can add another substream in OCE to talk about more system level challenges, which go beyond die-to-die interface, both the PHY and digital portion of it. Or we use the slice and dice the problem and put it in the existing groups so that we don't have to overload with another group. Or we say we are in a priority, which we have a lot of other problems. Let's address those more electrical and more die to die, and then we work on it. I am in the first bucket, given I feel this will inhibit the growth of the chiplet, which we want to see, where we have a focused work stream which can talk about it, identify it, and then bubble up. But I'm open to discussions. I just want to put all the options on the table and brainstorm.
No, this is really good because, there's lots of people on this meeting who work on different portions of what you have here. But what you're looking at is at the sum total and collective and the issues that arise when you're putting it together. Not just, as I keep asking, at the file level, but at a higher level of abstraction where it's the software, firmware talking to the hardware.
Yes, beyond the file level, because I know there are a lot of groups which are working on it. So anything which goes beyond the D2D interface, and it requires more, not even solution space, but the problem statements and identifying it and creating a document with those. That itself requires a very focused group, in my opinion, based on my just one project learning.
Right, I agree.
Hey, Durgesh. This
Hi,
is Raghu. I'm just coming on video just to show my face. No, it's good. I'm glad you bring up the system level aspects. I just, there are definitely many ways to go through that. But have you started looking at any of the EDA tools that may start kind of modeling some of the challenges you're facing at a high level?
Raghu, that's a good point. We briefly talked to EDA vendors, but that's a good point. Again, there's a small team. We didn't have that much flexibility or people to go look at it, but that's a very good point. So again, Substream can look at it as a solution.
Okay, thanks.
And Raghu and Patricia, the work that you guys are doing on the HPC modularity workstream, I mean, that, Raghu, when you talked about the software, that's a place where we're looking at some of the software that can help model the system. Of course, the first step is how do you disaggregate a system? Here, the disaggregation is clear, and you're moving on to the next level. So I think that some of the work there could also potentially help on the system level.
Absolutely.
Yeah, and I think one of on his slide, one of them talked about the modularity, scalability, and modularity. I think it was. I don't remember. It was on one of your slides, Durgesh.
Yeah,
there you go. I think maybe there's some connection, right, Raghu, between what Patricia's team is doing.
No, absolutely. No, I think, that's definitely true. And thanks for bringing it up. And that's the reason I was asking as to where we start the problem solving, right? So, Durgesh, I mean, maybe there are many ways to solve it, many different ways to solve it. You had like 3 or 4 options, and maybe like at the system level, maybe you might, I don't know, maybe you can think at the physical level to see how you bring it together. But I'm wondering, ultimately, we need to do some modeling of this, right? That's the reason why I asked the question. Is EDA a place to start? Maybe not, but that's why I was trying to kind of brainstorm how we can. It's a brainstorming question, right? Where will you start if you were to start someplace?
It's a good point. I think that's where collectively we have to decide how we do it, because different people have different expertise, and listening to all the ideas helps.
Okay. I mean, there is a lot of, in the Chiplet Summit, I came across a lot of good presentations from EDA vendors that, at least on paper and PowerPoint, they claim that they can do many of these kind of chips, system level designs. But I think we need to put one of them with your maybe use case as a kind of a pilot to go check to see if that can be done or not. That could be one way to do it.
Yeah, most of the EDA flows are old and clunky. They don't do things like thermal, and nobody does DVFS.
Yeah, I think, Kevin, that's true. But I think what I'm trying to say here is there are tools that look at performance optimization at the architecture level. If that could also fan out to providing data for other tools to take on. So I understand that tool has nothing to do with thermals or any of the reliability concepts. But data from there in some intelligent way farms out to determine if you even feasible, right? Now you've got two hotspots sitting next to each other and you're going to blow up everything. At least a first level analysis like that.
Yeah. Well, I was talking about that at the Chiplet Summit. Basically, you can start from like, what's your software workload, rather than like starting with what your chips look like, and say, okay, how do we analyze the workload so that we can break it up into things that can be assigned to chips, and then how do we wire the chips, and start at the software end.
Right, exactly. I think Patricia has a question.
Yes. So I think one of the things that I like the most about your presentation, Durgesh, is that the fact that you have an example-driven exercise, I think, and that puts a lot of context in the problems that we're trying to deal with. And I think that's one of the things that we can try to do especially in the HPC and AI modularity workstream, where we can have an example where we can take it all the way from the beginning to the end. I mean, I understand that fabricating is expensive and maybe we don't need to go there, but trying to pinpoint one example that we can design and replicate and try to start tackling all these little all these smaller chunks of problems in a particular practical way would be really helpful. Instead of having it in the in the abstract.
Yeah, I agree. And just detour, but yeah, I was surprised automotive guys called their ADAS as HPC, and you and I come from same background. We call the HPC as in really doing the weather and oil and gas, those kind of things, but they start calling ADAS as HPC as well.
This is ADAS in the car itself, or this is the kind of all the work that does in the all the training they need to do in the data center to even get to a kind of ADAS model.
So all the sensor fusion and then taking the decision out of.
Okay. Okay. So runtime dynamic in the car, they call that HPC. Okay. Fine. Terminology, but regardless, it's very regardless critical for them. So yeah, no problem. Yeah. Okay. Got it.
Presented at the Global Summit, Raghu, they had the one slide, and that one said they were talking about the ADAS system, and it was HPC, data center performance requirements with lower power, higher reliability, and all the good stuff that automotive requires. So it was HPC with even more stringent requirements is sort of how I understood it.
Okay, no, fair enough. I just wanted to clarify whether they're talking about the front end or the back end, but runtime, but yeah. Okay, go ahead.
No, there's no disagreement. It is just surprise more like, because I came from the Xeon world where HPC was weather and oil and gas and medical, all those things. And then, I mean, Intel used to call it as data center on the wheels. So I understand it. It's just a funny thing that when I heard HPC for ADAS, it was just surprising.
Yeah, I also heard the same thing, that I was talking to IMEC, that they feel that the data center, like Manu, what you said, with better reliability and safety moving in for the automotive world. IMEC uses HPC.
Yeah. So Anu, that's all I had. There's a recommendation. I think we will have to do some work in the background and figure out how you and Jawad want to do it.
Yep.
Yes, as Luisa was saying, I can provide a lot of real life examples on the product I'm doing. It's just one product. So yes, having input from others and other experts would be useful.
Yeah, no, absolutely. I think this was really great because as Patricia said, we've seen the lower pieces, right? The details and but we've never seen an example of a system being put together with chiplets from two different vendors other than HBM systems so far. So interesting to see how all the issues that come up with this and how we can use some of our existing groups, like the HPC group and then Rajesh's test group, to include, looking at the system level, not just at the lower die-to-die file level, and then look at further work streams that we may need, like the system level one you're talking about, which we're going to recruit you in a big way, to look at higher level issues. I really appreciate it.
Yeah, let's brainstorm if we should form a separate group for it, with more experts on the other system side of it. But let's brainstorm whatever is the best is good.
Yeah, and the security. So those are the notes I've taken. One is with Rajesh, Patricia, security, and then the system level. So lots of pieces here which we can fit in or start new work streams as we deem necessary.
Yeah. Okay.
Any other questions for Durgesh?
Before you go, this is Michael Durkin. I just have a 30-second update for you. As of last night, JEDEC has published the latest version of the JEP 30 part model, which includes the structure for the design kits. So we encourage you to take a look at that and to and again, once again, to have IEEE collaborate with JEDEC as we move forward on the development of design kits with the TSMC structure. So I cleared that with the JEDEC office and also with OCP, and the invite will go out later today to the JEDEC, to the IEEE office, to invite them to collaborate with both JEDEC and OCP on the future development of this.
Thank you, Michael. That's truly awesome. That's really fantastic that first it was a JEP 30 and then now they're coordinating the IEEE. So I appreciate that update, Michael. Thank you. So I was very ambitious where I said we would tackle another topic like the proof of concept, but I think the important thing was this was really good and to get us thinking of the different aspects which we haven't been able to focus on so far. So we will push the proof of concept out for another time. Next week, I will send out the agenda, but I believe I have another speaker from On Semiconductor. And he actually talked at the Chiplet Summit and I thought was really interesting. It is the other end. So this is not AI, ML. This is how do you combine what he calls more than more devices, which are ones that are across different processes, technologies, which are 22 nanometer and above. Does it make sense to go chiplets? What are the advantages and some of the cases that On has looked at? So I think given that we're looking at the bow down to IoT and 1 gigabits per second and lower data rates, I thought it would be really useful for us to look at that too. So, but I'll send the agenda out. Thanks everyone. We will have a day where we talk proof of concept, a little more detail. Hopefully we can get JP into the meeting. Otherwise, 1 minute left to end. Thank you very much, everyone. And for those who have a long weekend, enjoy your long weekend.
Thanks, everyone.
Thank you, Mr. Durgesh. Bye.